Let's welcome the second talk by Christoph Englert, talk about the Higgs phenomenology and opportunity for new physics.
Thank you very much for the invitation. It's my first time to Taiwan. So far I'm enjoying it fantastically. The weather is much better than Scotland, where I'm from. We do very good whiskey. Comes at the price of bad weather, but I found out that you actually do very good whiskey too. So that sort of puts my home country of choice a little bit to shame. Anyway, I want to talk a little bit about Higgs phenomenology as an opportunity for new physics, and there's a little bit of, I don't know what that means, but anyway. This is not working. Minor technical difficulty. All right, yeah. Thank you. Right, so let's see where we stand. It's 7 years after the Higgs boson discovery. So it's, the dust is settled and a certain picture has emerged, which is by no means trivial in any way. But we have validated all our mechanisms that we have in our quantum field theory toolbox. Okay, so as Coleman and Mandela showed in the 60s, late 60s, we roughly can discriminate symmetries in our standard model perturbative quantum field theory box into external symmetries, the representations of the Lorentz group, and internal symmetries, the SU2, SU3, and U1. And today we understand that massless vectors, so vector representations of the Lorentz group that are charged in a linear way under gauge symmetry, those will remain massless to all orders in perturbation theory, which is really the deeper reason why we impose the gauge principle these days, or just really pave the way. We know that massive and light fermions are protected really from chiral symmetry and marginal Yukawa couplings. And then the only player left in town were the weak interactions mediated by massive vector bosons. And my named colleague, Broud and Englert, okay, so I have no relation whatsoever to this person. But also my Scottish colleague, Peter Higgs, they sort of, as three people amongst a group of many, really showed that this is the only way how to non-linearly realize gauge symmetries, thus breaking electroweak symmetry. So nothing's really broken, but it's just realized non-linearly. And that nonlinear realization is That nonlinear realization is then compatible with a large vacuum expectation value of what is called the Higgs level. Okay. So we have validated everything that we can accommodate in the standard model Lagrangian, or in Lagrangians in quantum field theory in perturbative sense, that we have in our toolbox. So the question really is theoretically what's next. And of course, in comes here the Higgs boson discovery. And of course, a lot of measurements happened after that in 2012. So I lifted this from the last Atlas preliminary combination that they had with roughly 80 inverse femtobarns. And these measurements here of kappas is essentially the observed coupling divided by the standard model expectation. So the Higgs kappas to Z, so W's to the top to the bottom, to taus, and to gluons and gammas through loops of massive charged particles under QCD, or electrodynamics, so chops and W's. Right, and if the standard model was correct, then you would expect that all these measurements line up very nicely across one, and actually they do. And to some extent this was already anticipated from studying LEC data, but LHC is really pushing the envelope now, and we start to understand a lot more than could have been anticipated from the study of electric position data. But it's important to note that when we move each and every one, so if everything is consistent with one, but only one of them goes away from unity, then there is a need for new physics, because all of this is built self-consistently in a quantum field theoretic sense, which means that if I change one of the couplings away from the standard model, I run into deep, deep trouble related to unitarity violation and violations of the gauge principle, and all of this goes hand in hand. So nothing suggests that there is new physics here as yet, but we know that the standard model has shortcomings, so there's a lack of CP violation, so it doesn't explain why we have this nice conversation today. We have the hierarchy problem, which I think personally is still quite a massive issue that needs addressing. Could really point towards new physics, but we don't really understand these days what to make of it. But most importantly, there's also one coupling missing here, which is the Higgs self-interaction. Okay? So we have not seen, or we do not have as yet very good constraints on this particular interaction, because the production cross-sections of two Higgs bosons, which you require to set constraints on the Higgs coupling to itself, that is a very rare process, so it's very difficult to set constraints at this point in time, so we have to be a bit more patient. So the question now arises, can Higgs phenomenology point towards physics beyond the standard model? And you have to answer two questions in order to really gauge whether that's possible. So you have to address the question, why haven't we seen anything yet? And of course that feeds into a new physics benchmarking program that feeds into the physics case of the LHC at large luminosity at 3 m², which is really the target luminosity of the LHC lifetime. And the positive outcome of this question really depends on three ingredients. First of all, it's the precision at which you can extract Higgs couplings from measured data, assuming the standard model is correct. The sensitivity of exotic Higgs searches, so if there are new scalars mocking about, then we should better try to find them, or or at least explain why we haven't seen them yet, instead of just making them heavily coupling it. And of course, there's sensitivity to rare standard model processes, for instance, Higgs production, which I motivated in the previous slide. And of course, the answer to all these three questions and the extrapolation to the 3 m² case then makes contact to whatever kind of future experiments we can envision. And I want to sort of go through these three questions, pointing out what has been done recently to make progress along these three lines really of investigation. Right, so let's first focus a little bit on new ideas to improve Higgs coupling extraction from measured data. So Higgs coupling extractions are made difficult by blind direction. So if you look at all possible deviations of Higgs couplings to standard model matter, you have like order 10 different parameters that sort of you need tension against each other. And the most famous one is probably the one that John Ellis and collaborators used in the 70s after a Russian group to do their first investigation into Higgs phenomenology, really is decoupling the top quarks. So if you look at Higgs production from two gluons, it is mediated through a top loop. The bottom loop is completely negligible here in the standard model because the bottom mass is so small compared to the top mass. And because the Higgs coupling to the tops is proportional to its mass, it doesn't really decouple when we send the top mass to infinity. So if we send the top to infinity, you see that this is actually a contact interaction between the gluon field strength tensors and the Higgs field. Okay, so it's a low energy effective theorem. So if I now start modifying this coupling here, I can equally well compensate for this effect by introducing a contact interaction that might be mediated by additional tops that float about in the spectrum of our theory, which happens, for instance, in composite Higgs theories. So contact GGH interactions really mask top-Yukawa interaction measurements, and this is really one of the biggest issues that we face, especially when we want to make contact with, say, composite Higgs theories or two couplet models, for instance, which I'll talk about in a little bit of detail later. The way out, as we all know, this is really the name of the game of particle physics, is that you introduce a new energy scale to your process that resolves the Compton wavelength of whatever is going on in the middle, right? So essentially, you try to probe this interaction at a momentum transfer that resolves the top mass here, which is of course inverse proportionally to the quantum wavelength at the top. And in order to do this, you have to radiate off additional jets or additional gluon xenon. So this is out of battery. But in order to do this, yes, you have to radiate off additional jets, 1 or 2, and this is where it becomes a little bit more tricky. Okay, so I produced this plot here just to highlight what a blind direction really is. So I chose the coefficients of these interactions. So the big circle will be the contact interaction. The little blue dot is the interaction of the top with the Higgs boson. And you can sort of tune it in such a way that the inclusive cross-section, without any additional jet radiation, is completely standard model-like. But if you feed this in as a choice of a cancellation of CG versus CT, which really just steers the relative size of these interactions, then if you go high enough in jet emission PT, then at some point you can see that your new physics model starts to deviate from the standard model, as you would expect, because you're probing physics above the characteristic energy scale that is apparent to one of these couplings, namely the top mass. Okay, so but of course physics is never a central value game, and you have uncertainties attached to this. So uncertainties related to systematics from the experimental side, but also theoretical uncertainties, because we can only do this calculation in fixed order perturbation theory, plus some additional improvements. So really going out here to 500 GeV, for instance, where these curves start to deviate from the uncertainty band, is a costly thing, because the cross-section is reduced by 3 orders of magnitude. Okay? And if we face problems like that, then our experimental colleagues typically invoke multivariate techniques, boosted decision trees, really hone their analysis in a highly nonlinear way to gain sensitivity. And of course, if you radiate off more jets, this is a 2-to-2 process. At parton level, this is determined by 2 observables. One is the center of mass energy, the other one is the pseudo rapidity of these jets. Then you have nailed the problem. So if you have more jets, you have a smaller rate typically, but you also have more kinematic information, and you can use this really to get to the bottom of it. So if we try to mimic this in a machine learning type of approach, which has become particularly motivated over the past few years, you can train a neural network that starts to distinguish between the standard model and your new physics scenario that I showed in the previous slide. This is now for the 2-jet case, exactly for parameter choices which roughly correspond to this blind direction. In the units, it doesn't matter. But you can see that these neural net algorithms, where you train really a plethora of kinematic observables, and then your computer algorithm starts to learn what is new physics and what is old physics and boring physics. So new physics is clustered here at 1, boring physics should be clustered at 0. So this is really discriminating between the standard model and your new physics scenario. And of course, the most sensitive regions of phase space, where you start to see deviations of the two, statistically significantly, those are particularly susceptible to uncertainties, and as you can see, by just varying the scale as we traditionally do in particle physics. So if I change my renormalization and factorization scale by a factor of 2, I move these standard model curves closer to my BSN peak here at 1, which means that I can't discriminate so well between the two anymore. So the question now is, how can I be sure about the confidence level that I set here? So neural networks are extremely, extremely good in discriminating between different scenarios, but they are also very susceptible to theoretical and experimental uncertainties. Okay, so this is of course what we want to avoid, and it sort of gives it away here already what comes next, because we can plug into this algorithm a new, a second neural network that starts to penalize the first one once it gets sensitive to your uncertainties. Okay, so this means that I penalize the classification into new physics and old physics if that classification becomes very sensitive to our scale variation and the intrinsic theoretical uncertainty. So you implement this uncertainty knowledge already at the stage of the training, which means you actually get now a very robust discrimination between new physics and standard model physics, which is highlighted by these three curves really merging on top of each other. So it's not three isolated hums for three different scale choices, but irrespective of what scale I choose, the discrimination between new physics and old physics will always be the same. But of course, it comes at a price. That you have a double peak structure here, which tells us that in a region where the two curves, ESM and standard model, overlap, in a given uncertainty band, no discrimination is possible. So discrimination will be imperfect, which it should be, and this is exactly shown through this here. So you get a very robust discrimination between new physics and old physics, but this comes at a price, of course, of a slightly smaller sensitivity. But that sensitivity is still the highest possible, because you train it on not really with rectangular cuts in your phase space, but through dedicating regions that are highly sensitive to new physics, but not sensitive to your scale variation or your systematic uncertainty. So if you compare this now to the old approach, where your confidence level or your significance to new physics, when you approach the blind direction and you go to zero, you have exactly this cancellation into a cross-section. So you can see sometimes, depending on how your Wilson coefficients or these new couplings are chosen, it overlaps with the traditional approach, but sometimes it's just much more conservative, okay, but more robust. So these give really rise to the most robust yet most sensitive constraints that you can set on Higgs coupling extractions from LHC data. Right, so I want to move on to Dieck's final states. So this was 100 inverse femtobarn. This is where these things become relevant. And of course, if we go to Dieck's final states, so we have 1,000 picobarn cross section at the LHC for Higgs, single Higgs production amongst friends. For double Higgs production, it goes down to 32 femtobarn inclusively. So naturally, if you want to see that process in a highly busy LHC environment, we are pushed to very large invariant, to very large statistics, so large luminosities. So this is a CMS extrapolation to 3 inverse autobahn at 14 TeV. And you can see that we just barely touch, really. So this at 1, this would be the standard model. Okay, so this is the Higgs self-coupling variation with respect to the standard model expectation. And this is the theoretical prediction. If you only start playing around with the Higgs self-interactions, you can see that you become sensitive to the standard model, but not much more than that. So the question really is, what can we gain from this? And so Dieck's production is really the first process where you can start probing Higgs self-interactions. As you can see, you want to get hold of this particular vertex here. But of course, processes are always correlated very much with single Higgs physics as well, because you have to radiate off the first Higgs from the tops to dominantly produce 2 Higgs final states. And of course, it's relatively straightforward and beyond the standard model scenarios to crank up this rate. Okay, so for instance, in composite Higgs scenarios, in a nonlinear approach to that, you would nonlinear effective field theory, I should rather say, you can introduce interactions of this type, which really break the correlation between single Higgs physics and a large di-Higgs ray. So it's very difficult to sort of make contact with the Higgs self-interactions once additional stuff is going on. And it's very easy to get large and exciting rates in ad hoc EFT. But most of these rates will be difficult to be physically meaningfully adaptable to concrete or ultraviolet scenarios. Okay, so if your effective field theory deformation does not correspond to a particular ultraviolet scenario, then it's pretty much worthless, and you're essentially just chasing your own tail. So matching is really an important business here. So we decided together with Sally Dawson and Margarete Mühlleitner and her student Philip Arthur to take a slightly different approach, but and use concrete Higgs sector extensions. And here we focus on the complex 2Higgs doublet model and a complex singlet extension to try to sort of reconcile all the shortcomings that we see in the standard model through a dedicated parameter scan. This means we have a look at 125 GeV Higgs boson signal strength extrapolations. So we take whatever we can find from Atlas and CMS, extrapolate this through 3 inverse autobahn. We use ECFA study for that as well. We have exotic Higgs searches, you can extrapolate those as well to 3 inverse autobahn. And then inject additional theoretical constraints like the electron EDMs, flavor constraints, perturbativity constraints on the extended Higgs sector and potential, can require strong first order phase transition and CP violation. So we just try to make sure that we cover all our bases and really find a theory that is compatible with all the observations that we have. And then we can ask the question really, is double Higgs production still a relevant problem? Okay, so here in this picture you would say, okay, we can crank up the rate and you can set nice limits on coefficients that you introduce, like the Higgs self-interaction or additional processes that modify your 2 Higgs final state rate. But the question really is that physically relevant? We just approach this from a slightly different angle where we inject all experimental and theoretical constraints and then ask the question, is double Higgs production still a relevant process? And so fast forwarding, I don't want to go through all the details here. What we see is that, so I just probably should explain what this means. So the exclusion luminosity is a definition that we introduce that denotes the luminosity at which your standard Higgs searches, single Higgs searches, Higgs signal strength searches, exotic searches would start to see this moment. Okay. So if you push this out to 3 inverse autobahn, then really only double Higgs production sits there as a candle for new physics. Okay. So you can see that really this sticks here in the production of 2 Higgs bosons in the decay to BB bar gamma gamma, one of the golden channels for double Higgs production. It really drops close to 3 inverse autobahn, and this is a signal of TT bar final states becoming important here. So you can see exotic states coupling to top quarks, and then TT bar resonance searches really become very important. Of course, if you see it in TT bar first, then double Higgs is not really like the first process that you would flag as a beyond the standard model physics candle. But you get nice enhancements before that. Okay, so there is a lot of interesting physics that's going on here, and typically that amounts to multi-resonance structures that you have in the complex Higgs doublet model. So there is a whole load of neutral scalar bosons floating around, all with CP violating couplings, and they produce these nice and interesting multi-resonance structures. And at the same time, you can address the effective field theory limits, so you can couple your new fields, and you'll find actually that in the context of perturbative complex 2 Higgs doublet models, you don't really gain anything from EFT deformation studies in the Higgs sector so much. So you saw I alluded to the top pair production processes being very, very important for these particular searches, extra Higgs bosons. But at the same time, it's also easy to overestimate them. And that comes due to large interference effects between the Higgs signal and QCD background. So that's known since the 80s. So if you look at this process and just look at the TT bar production here, so you produce not the standard model Higgs, but some other Higgs with CP violating couplings to the top sector, you would get some nice bright Wigner peak here, where this is set essentially by the lifetime of the Higgs boson at transient ES channel. But if I switch on the backgrounds, and the discrimination between signal and background is arbitrary, one has to be very, very careful, because it typically violates gauge invariance and unitarity by just treating a subset of Feynman diagrams irrespective or completely independent of the other ones. That's a different issue. But if you switch that on, actually what you find is not a peak structure, but something that looks really, really nasty and difficult to observe experimentally, because our statistical tools are designed specifically to avoid downwards fluctuations in data. So if you have a dip structure like this is very difficult to observe at the LHC, and that comes on top of a huge TT bar background as well. So that comes from a destructive interference effect between continuum TT bar production and Higgs production. So you can see that the narrow width approximation, so you produce a Higgs as a cross-section, you decay it into a TT bar final state with a branching ratio, is completely inadequate to estimate the significance of such a process. So this is bad news, but it could also be an explanation why we haven't seen anything yet. At the same time, you can now ask the question, if we can't see anything in TT bar production because we have this destructive interference effect, does that sort of play into double Higgs as a discovery mode for these new particles? And it actually does. So if you compare the actual cross-section divided by the sigma times branching ratio estimate in the type 2 complex 2x doublet model, for all these points that satisfy signal strength constraints, etc., you'll find that always you get destructive interference in TT bar. So this is actually always lower than 0 and always negative. Okay? So you get a reduction of rate rather than an enhancement. So this is really quantum mechanics at its best. But at the same time, if you look into double Higgs production, you actually can get an enhancement. So even factors of 2 here, when you would never see anything in TT bar production. So why is that the case? And that comes due to these constraints that we invoke on the Higgs sector, really favoring, and that's a typical thing that you see in 2x doublet models, favoring nearly degenerate resonances. Okay, so TT bar, for instance, here you can see you have this dip structure now if we switch on interference, just like I showed in the other on the other slide. But you have 2 resonances that are very, very close to each other and not necessarily experimentally resolvable if you think about experimental uncertainties. So this is a signal background interference effect. In double Higgs production, the continuum Higgs production is very small at this point, and what you really see is signal-signal interference. And that is often actually a constructive interference effect. So again here, your sigma times branching ratio estimate is completely off, but this time to signal-signal interference. And even if you can't discriminate them experimentally, and you would see a single peak, hopefully we see something, but if you see a single peak in double Higgs production, and you want to interpret it along the lines of 2 single bosons rather close to each other, which is completely possible in a complex 2x doublet model scenario, then you would need to take this still into account, otherwise you'll get the wrong constraints on the microscopic parameters of your theory. Right, so in the last 5 minutes or so, I want to say a few words about future collider physics. And this is always a little bit of a thorny issue because you're very much victim to the assumptions of your systematics. Okay, it's very, very hard to make claims that are not unfair to one of the other concepts. Okay, and a strawman scenario that people have used in the past, and Jörg Jekyll from Heidelberg and I did the same, used a Z2 symmetric Higgs portal. So it's very straightforward Higgs sector extension, where you protect the new scalar with a Z2 resonance. So it only couples to the Higgs in pairs. So you have a Higgs SS vertex. So this means if the mass of that scalar is larger than mh divided by 2, you do not have additional decays of the Higgs into these states. And then the only way of seeing them is through modifications via loops. Okay, so you break standard model correlations through additional radiative corrections, or you can kinematically produce them through a Higgs propagator. And then you can say, okay, this is sort of a fair comparison because I can tension then higher energies at the LHC against the precision of ILC. So it's direct sensitivity, but it's not direct sensitivity when you offshore produce these things. Right. So how does this compare? If you plug this additional scalar into Higgs production corrections, you get final diagrams like this. You have to worry about tadpole renormalizations and all these sorts of things, but it's technical, which is not really important. You have Higgs position studies at colliders, so you have your field strength renormalization and your LZ factors associated with the Higgs in the on-shell scheme, for instance. And you have off-shell production, where you can have, for instance, Higgs production, and then you off-shell produce the standard model Higgs, and then decays in not expressed as verbis, but It's off-shell produced and decays into two of these scalars. Okay, all of these, that's typically a process. You can observe this at click, or you can observe this at FCCHH. You can observe this at the FCCHH. This is probably more something for precision Higgs machines, like a lepton collider. Right, so very complicated plot. We'll show all of these things, okay? So the solid lines here is the discovery reach in this model as a function of the scalar mass and this additional portal coupling. Right, and the solid line is really di-Higgs production at the FCCHH using yellow report, thank you, as an input. So this amounts to 6% measurement of the double Higgs, of the Higgs self-interactions that we convert into a big log likelihood, and then set constraints on these models. So double Higgs production works very well because there are really two effects. It's a threshold effect, but you also get a modification of the continuum, which is twice as large as the single Higgs production. So this is probably fairly optimistic, and you can see di-Higgs production at the LHC is not there. It's not even in the region where the electroweak potential would be stable. You have a whole range of other things going on here. So this line, for instance, compares to FCCHH off-shell production, where you produce these additional scalars through an off-shell Higgs. And all these colored scenarios, they contribute to different percent level measurements of the associated Higgs production at FCC, EE, at click, or at the ILC. So you can see there is a sort of a trade-off. If I decrease my LHC sensitivity, I can get back into the region where there's a nice complementarity actually between FCC, HH, and FCC, EE. Okay, so brings me to my summary. So Higgs physics is really at the heart of our VSM efforts, and it's on a good way. I didn't talk about enhancing theoretical predictions, but this sort of underpins all of this, of course. I'm personally not working in that area, but that will be crucial in the future as well. But at the same time, we learned through adapted machine learning techniques to avoid uncertainties where we can at least model them. Okay, so you can improve your null hypothesis, or you can avoid being sensitive to the uncertainty of your null hypothesis, which is another way of improving the quality of your analysis. And secondly, there's an opportunity to link the Higgs sector to new physics, as always. So we can cure standard model shortcomings such as CP violation, and multi-Higgs production is really a hard case for BSM sensitivity. You see this in concrete scenarios and maybe in more goofy models like this Z2 model. And new collider concepts can maximize the precision versus energy reach in really complementary ways. So without making a preference to one of them, they have both their merits. And it would be great to have both, rather than only one. And that's me. Thank you very much.
Okay, so we have one or two questions. And can I just press this one? Yeah.
Well, yeah, so that Strawman is a very pessimistic Strawman.
The what is pessimistic?
The Strawman scenario, right?
Yeah. Well, that's on purpose, right? We tension something which you actually can't really see. You can't really see it at hadron colliders. You can't really see it at lepton colliders. You can only see it through virtual effects.
Why do you want to choose such a?
Because it's fair, right? It's fair. Because
why is that fair?
Why it's fair? Because if I
this undersold. I mean, I think it's undersold cells.
It's a model, and then you make predictions, right? And
so
then
you expect the Z2 to be broken at some level, right? So this will the singlet will decay. Will give you much better signals.
That's right. If you have the energetic coverage, right? If you have the energetic coverage.
Yeah, but I think the problem for the NTHU, for example, for this guy is if you just produce it with Higgs, the rate is not great. But if you only have to rely on the missing energies, then that's very difficult.
Yeah. Right.
But you do expect the Z2 to be, even though it can be approximate, but it will be broken at some level.
Yeah.
Right? So I'm just saying, what do we think is fair, right? It's not fair to say this give us the hardest life possible. That's not fair, right? We want to estimate the prospect of some future machines. Right? If you want to take somewhere in the middle, I think even you wanted to have Z2, I think that we should sort of think about the Z2 as some kind of approximate solution, and then the S will decay, even though it does not change your minimization at all. Right? But S will decay, even just break at some very small level. That give you much better signals.
That's right. That's right. And I mean, that's a little bit the idea where I came from, right? So what I'm trying to say is that let's imagine that we give this color charge as a straightforward case, right? Then it's FCCHH because it just produces.
You not even just take this model, add a little bit of Z2 breaking. That's already much better than
But then it's again a clean cut case, right?
Yeah. Okay. I think you can debate
the case is really clean cut.
Yeah, but then if you have a Z2, so that you can also talk about a dark matter, that sort of thing. Well, of course, if you don't want to talk, then you break it anyway. Okay, so let's thank the speaker again.